All right, here we go. McMurray, section 16.6, nucleophilic aromatic substitution. All right, this discussion relates to section 16.6 in our textbook. It's nucleophilic aromatic substitution. Now, when we discussed electrophilic aromatic substitution, which is the reactivity patterns we've discussed so far, what was the role of the benzene ring? Well, in electrophilic aromatic substitution, the role of the benzene ring is as the nucleophile. In nucleophilic aromatic substitution, the role of the benzene ring is going to be reversed. It's going to be the electrophile. And so all the patterns of reactivity that we've learned thus far will also be reversed. But if you can just make that distinction, and as I've emphasized all the way up to this point, recognizing nucleophiles and electrophiles, acids and bases, these pairings are critical to understanding the chemistry. So let's look at a classic nucleophilic aromatic substitution. If we have trinitrochlorobenzene and we treat this with sodium hydroxide, we make picric acid. That is trinitrophenol. This is a very, very acidic alcohol. TK is down around 1 or so. Don't quote me exactly on that number, but it's in that region. So this product has those 3 electron withdrawing groups, as did the starting material. And in fact, those strong electron withdrawing groups at the ortho or para position are a requirement for this. Okay? They're absolutely required for nucleophilic aromatic substitution. Now, this reaction is going to have a different mechanism. It's going to be an addition, elimination mechanism. And we'll see what that is in a few minutes. But first, let's address this scope and limitations issue. So if we consider the following, substitution, with only one nitro group on the chlorobenzene, again with sodium hydroxide, we need 130 degrees C to get a good yield of product. Okay? It works. If we take the para compound, and those single quotes or squotes mean to bring down the conditions from above. Just makes things go a little more efficiently for us here. Again, we get good, efficient substitution. To produce the paranitrophenol. But let's now consider the other isomer. Can you draw the third isomer where the nitro group is in the meta position? Sodium hydroxide, 130 degrees Celsius. We produce this, but we do not get the product in this case. There is no reaction. So there's a huge difference based on the stereochemistry and placement of those electron withdrawing groups. Now, why is that? Well, I hope by now you've learned enough of the mechanisms of these reactions that you can begin to speculate about why this would be the case. But let's take a quick look. We'll use the para for our example. Here's our nucleophile. In this case is going to be hydroxide. We know it's the nucleophile because it's got lots of lone pairs. Okay? Nucleophiles have lots of electrons. This is an electron deficient system, and I'm going to push a couple of arrows here to make it obvious from the beginning why this one works the way it does. So the nucleophile attacks the carbon ipso to chlorine. Remember ipso. And then I'm going to push a few arrows here. Okay. We produce an intermediate. That one's not putting out enough ink, so. Now, I'm going to draw out the nitro group this time. Remember, the nitro group is strongly electron withdrawing. Remember, balance the mass, then balance the charge. I brought in an anionic nucleophile that made my mechanism anionic, so I need an anionic intermediate. Now, for those who are worried about electroneutrality, of course, there is a sodium ion floating around in there with this, and the same would be true here. Okay? But the critical thing here is to see that there is a resonance form of this compound. Can you draw that resonance form? Pause for a second and try. Here is what that resonance form would be. The lone pair can don't resonate out to nitrogen. That pi bond swings up. We now have a compound I'm slipping off screen. Let me slide over here. Come back and edit that out. Take that segment out. Coming back now. So there's the full resonance form, and you can see how that anion is especially stabilized because of the presence of the nitro group in resonance out to this position. Okay, so this was the nucleophile attacking. That's the addition part of the mechanism. And now the elimination, and I'm going to push a bunch of arrows here. Now, again, I'm not sure how much we've discussed so far this semester of our 3-arrow rule. Normally we don't push more than 3 arrows unless we have a special case of conjugation, and this is one of those where I have a resonance form and now my leaving group leaves, and that of course produces the desired or the obtained product. And that's one of the key principles of pushing arrows. The correct mechanism gives the observed product. Okay, so that's a caveat you should take home and store in your bank. The correct mechanism gives the observed product.